Okay, so good afternoon to all. Everybody, please go to mute mode until and unless I ask for unmute. First, now I have shared today's lecture note, and I hope it is visible.
Yes, sir.
Yes, sir.
So, in the last class, we did discuss about how to develop theory for quantum physics. And in fact, we did discuss by giving qualitative arguments. Means we play around de Broglie hypothesis and uncertainty principle. Then we said we need to have a probabilistic approach in order to develop theory for quantum particle. And then we said that there must be a wave function associated with the quantum particle or a quantum system. The wave function is, like trajectory in phase space for classical particle. That means the physics based on deterministic approach or Newton's law called classical physics. And here for quantum system or quantum particle, we have wave function. And then we studied some of the important characteristics of wave function. Some of them are like, the wave function must be single valued, it must be finite, it must be continuous, it must be square integrable, and the wave function and its fast derivative must be continuous everywhere, even including the boundaries or the interface of two media. And most importantly, it should follow an important equation is known as Schrodinger equation. So that was, the summary of the last lecture. Am I audible?
Yes, sir.
Yes, sir.
Yes.
So, so today we'll be discussing about more detail on Schrodinger equation. So, like we compared wave function with the trajectory in the phase space. Similarly, we can compare Schrodinger equation, its corresponding analogs in classical physics. So like in classical physics, we have Newton equation, that means the second order partial differential equation. So this describe motion or the trajectory of the particle. Okay. So the trajectory, if you remember, we have trajectory phase space, px, momentum and its corresponding x. And then we have a trajectory like this. And on this trajectory, we have point. This point indicates the state. Okay, and the pt, the state, for example here, the state of the particle. And then by using the Newton's second law, which is second order ordinary differential equation, because we have only one independent variable, we can get all these trajectory points on the phase space or states on the trajectory of phase space. So do remember, the points on this trajectory is known as states, XTPT, right? So it represents the state of the classical particle. So similarly, the Schrodinger equation describe the behavior of a system through wave functions. So like we have trajectory, and if we use Newton's equation of motion, then we can get the state or the other XT, PXT value on the trajectory. Similarly, we have Schrodinger equation, and when it acts on a system, and it will extract information from this wave function. Newton's equation acts on trajectory, you will get information. Similar, the Schrodinger equation act on wave function in order to get information. So this is the analogy between Schrodinger equation and Newton's equations. So in fact, the Schrodinger equation is a second order partial differential equation. Why? Because we have two independent variables. One is the position and the another is the time. Okay, at least two. If you have a 3-dimension, we have 4 independent variables. X, Y, Z, 4 coordinates per space, t is time. But the Newton's equation, we have only one independent variable, that means time. So if you have a momentum, it is a function of time, and then the corresponding this is so we have one independent. So therefore, the Newton equation is a second order ordinary differential equation, whereas the Schrodinger equation is second order partial differential equation. And in fact, one can show that it must contains the derivatives, right? The second order derivative with respect to the position and the first order derivative with respect to the time. Okay, so in principle one can derive in 3-dimensional representation. So let's look at the individual term or notation that are associated with the equation. What is psi r t? It's a wave function associated with the quantum particle or a system comprising quantum particle. And r is the position vector. R is I cap x plus j cap y plus m cap z. It is the time. And what is I? I is an imaginary number. And as we know, I square equal to -1. Okay. And what is h bar? The reduced Planck constants, which is h over 2 pi. M represents the mass of the particle. And this, a downward triangle with square, that represents Laplacian or Laplace operator. That means the partial derivatives, the secondary partial derivative with respect to the position, del square over del x square plus del square over del y square plus del square over del z square. So then you might ask question, let's believe this is the Schrodinger equation, but can we prove? In fact, we can derive. Okay, so that's I'm not going to do here, but still, you might be, like to know, you might be like to know that whether this is indeed the Schrodinger equation. Can you verify or not? Yes, you can verify. So what you have to do? We know the wave function, and for simplicity, we have one-dimensional wave function. And that case, we have a free particle. That means the underlying potential energy is 0. Vxt must be 0. Why we are dealing with free particle? Because first we'll verify for simplest case. Then we'll have 3-dimension as well as particle with potential field. So this represents the wave function. For one-dimensional wave function, a e to the power I k x omega t. And so let's get the derivatives and put here. Okay. So when we do the first time derivative with the position, I will have I k psi xt, and when the time we'll have minus I omega psi xt. But we know the energy is h nu, where is the Planck constant, nu is the frequency, and from de Broglie hypothesis, lambda equal to h over p. So so now we have k here, we have omega here. Okay. and we have in fact we can derive this relation h bar omega equal to h bar square k square 2m. That means the omega is appearing here, k is appearing here, and if we use this relation and try to combine this equation 1 and 2, we can probably get the Schrodinger equation. So that's exactly we have done here. And E equal to h nu, we know the energy must be quantized, and again h bar nu, h bar is the reduced Planck constant, lambda equal to h over p, p equal to h over lambda, h over 2 pi over lambda. H bar and 2 pi over lambda is nothing but your wave number k. Okay, and as I said, the energy here is h nu, and as you know, p square over 2m kinetic energy plus potential energy. Since we are dealing with free particle for simplicity, Vxt will be 0, p square over 2m, simply substitute the value of p, will be h bar square k square 2m. So now we have this relation. It means we derived by using this fundamental relation. Is this clear to everybody? Am I audible?
Yes, sir. Audible.
Yes, sir. Yes, sir.
So now, if you look this equation, so now you can see the k square term is appearing here, but we have only ik. So it means we need to have one more time derivative with respect to x. If you do that, what we'll have? We have this one, h bar square k square over 2m. And what we have relation this, and in order to get h bar omega, we have to multiply I h bar in equation 2, this equation. When if we multiply I h bar, so I will be I square minus I square over 1 h bar omega. So that we have here. So now since we have h bar k square 2m equal to h bar omega, so equating equation 6 and 7, we'll have this relation. Okay. So now, so if the particle is not free, what we have to do? We need to add here the potential energy. So that's exactly the Schrodinger equation in one dimension. I h bar del sky. So now we prove that the Schrodinger equation we have written down here is indeed correct one. So this is for 3 dimension, and in 1 dimension, here we have Ax, and here we will have a del square over del x square. Okay, so you have to replace r equal to x or z. So that's exactly we have derived here. Okay, so now verify. So in 3 dimension, as I said, we'll have this, and then we have derivative like this. Finally, we have this equation. So now we can trust that this equation 9 should be our Schrodinger equation in 3 dimensions. And if you look this Schrodinger equation, what we'll find that the potential, it varies over position as well as time. That means as time changes, the potential landscape will also change. But in most of the practical purpose, the potential landscape or potential energy does not change over time. For example, so let's say, we have, hillside or mountain, right? Since there is, different, landscape, and then the potential, it varies over position. That means if you go from one position to another position on the hill, the potential energy will change. But this potential landscape does not change over time. That means if you arrive, let's say, tomorrow or day after tomorrow, the landscape will not alter. It will remain same almost. So in that regard, the most of the practical purpose, the potential energy does not depend upon time. It means the potential energy is independent of time. And then if that is the case, and as I said, the most of the practical, application of practical purpose, the potential energy is independent of time, then the Schrodinger equation associated with that potential energy or potential landscape is known as time independent Schrodinger equation. Got it? So it means in order we have time independent Schrodinger equation, the potential energy should independent of time. That means it should be V of R. Therefore, we have time independent Schrodinger equation. And if this is the case, then we can use little bit mathematical tricks. That means the variable separation method. And what do we have? So this is in 3 dimension. We can substitute omega, as we know, energy equal to h cross omega. So you'll substitute E over h bar, and you can write down like this. And since this is possible because the potential energy does not change over time. So therefore, we can use the variable separation psi r f of t with psi r a1 e to the power I k dot r, whereas f of t a2 e to the power minus I e t over h bar. And if you substitute this psi r t in one-dimensional Schrodinger equation, what you have, right? So if you arrange the term, what we'll have finally this equation. The Laplacian operators psi r plus 2m h bar square e minus b r psi equal to 0 with psi r a e to the power I k dot r. This is known as time independent Schrodinger equation. Okay, so you can take this as a homework and you can prove it. You use this psi of RT, so this wave equation, and you have to prove this. Okay, or this is the complex form, or you can write a sine k dot r minus omega t, or a cosine k dot r minus omega t. You can write like this. Okay, so this is complex form and this is in sine and cosine function form. Okay, so what can we conclude from this time independent Schrodinger equation? That means when we'll solve most of the quantum mechanical problem, and in fact, we'll solve some of the notable exact solvable problems in quantum physics. There we will use or we'll begin with time independent Schrodinger equation because the potential landscape does not change over time. Therefore, we should deal with time independent Schrodinger equation. So is this clear to everybody?
Yes, sir.
So now we understand more or less about Schrodinger equation, and let's come back how we can extract information. That means how we can get the measurable quantities. If you remember, in the last class we did discuss about that the wave function contains all the information of the particles. That means whatever the measurable quantities we are interested to get, we can get from the wave functions, right? And that value is not well defined. That means not a precise or exact defined value. We'll have some percentage, right? Or in other words, the probability of the finding particle or probability of the energy at that particular position, probability of the momentum at that particular position, and that probability changes over time, right? And the Schrodinger equation, since it deals with time derivative as well as the space derivative, it explains how the wave function changes over time. Therefore, the relative probability of the measurable quantities means energy, momentum, and so on. So how we can measure these things? So let's study that. So by solving Schrodinger equation, we'll get the wave function in the next instant of time. But how we can get measurable quantities from the wave function? Okay. So in order to get information from the quantum particle or quantum system, what we have to do? Something should act on wave function, right? and that will give the measurable quantities. That something is known as operator and normally defined by capital Q bar, and these measurable quantities, okay, which will have certain probabilities are that instant of time is represented by small q, and this is known as, or sometimes you, instead of saying measurable quantity, sometimes people call physical observable quantity, because you can indeed measure physically this one. You can measure it, you can physically observe it. Okay, so therefore sometimes people call physical observable quantities. So do remember it, it gives the information of the measurable quantities, as I said, position, momentum, or energy at a given instant of time as well as at a given position. And if you solve the Schrodinger equation, it will give the information of the wave function in the next instant of time or next position. And we have to act by operator on this wave function at any instant of time in order to get the measurable quantities with certain probability or percentage. Okay, so let's look at, so what would be the measurable quantities that I have been talking so many times, and what would be their corresponding operator? In other words, so which kind of operator should act on wave function in order to get the measurable quantities? The energy operator is E, sorry, the observable measurable quantity is energy, that means the total energy, and the operator is I S bar del over del T. And the measurable quantity is the linear momentum, and the operator is minus I S bar this. And then the kinetic energy is the measurable quantities, and this is the operator. The potential energy is the measurable quantities, and it's also V is also the operator. So these are some well-known, operators and their corresponding measurable quantities or physical observable quantities. Is it clear to everybody? Yes or no?
Yes, sir.
Sir,
Yes.
sir, are these same operators in all dimensions?
Same operator in all
Dimensions 1D, 2D, 3D?
No, I mean, yeah, what? For example, here. So this is 3D. What is this symbol stand for? This is gradient, right?
Yes, sir.
I cap del over del x plus j cap del over del y plus k cap del over del z. So this is 3 dimension. In 1 dimension, if I say what would be the operator? It will be simply minus is bar del over del x. Yes or no?
Yes, sir.
So it depends on the dimension.
Okay.
So what I'm saying, that in order to get observable quantities, there must be corresponding operator. And again, I'm repeating, this is the wave function at a given instant of time as well as a position. And this, when I say at any given instant of time, that means arbitrary. And how will get this wave function? By solving Schrodinger equation. By solving Schrodinger equation, you will get time evolution as well as the space evolution of the wave function. And once you get the wave function, you have to, an operator should act to get the observable quantities, measurable quantities. The probability, the expected value.
Yes, sir.
Okay. So we'll
Yes,
work out some problem, then it will be much clearer. Okay. And
yes.
then, as I said, how we can get wave function when we solve while we'll solve Schrodinger equation, that we'll do in the next class. Some of the important, exact solvable problem in quantum physics. That means we'll solve Schrodinger equation, we'll get the wave function at different, wave function form, which must depend on the time as well as the position. Okay. So time dependent position. That means if you put the position, we'll get the wave function. If you put the time, we'll get the wave function. So therefore, an operator should act to get the measurable quantities with certain probability or some percentage. So then you might ask question that if that would be your probability value or some percentage of value, but once we do the measurement, let's say n number of measurements, right? So it means when we toss a coin, we cannot say whether the heads or tails will come, or simply when you throw a dice, we cannot say whether 1, 2, 3 or 6 will come. But if you repeat over time, then we'll say we'll expect something. That is called your expectation value, that we expect if you repeat this experiment over and over time. So when we do measurement, when you measure physical quantities, as I said, energy, momentum, position, kinetic, and so on, we'll get some probabilistic value. And again, if you measure, then this value might change because the probability also evolve over time as well as position. So if you measure again and again, that we should expect some final value, and you have, in order to get better accuracy, you have to average out it. If you take, let's say, n number of experiments and you observe different values, and if somebody asks what would be the final measurement, then you have to average out it and you'll say, look, so this is the final value. Okay, and that is known as an expectation value that we expect. Okay, so in quantum physics, when somebody do measurement, it is not that he measures at unique time or unique position, and whatever the information he or she get, that would be the final value. That's not correct. You have to measure again and again over time and position, and you have to average it out, and that would be your final observation. So is it clear?
Yes, sir.
Okay, so now, so this Q, so for example, at a given instant of time, the operator will act, will give the measurable quantities at a given instant of time or at a given position. Again, you repeat, you will get, let's say, Q1, you will get Q2, you will get Q3, you will get the Q4 and so on. But the probability, this Q1, Q2, Q3 and Q4, it is not same. For example, this will be, let's say, 0.1, this will be 0.15, this will be 0.05, this will be 0.3 and so on. And so when the total probability, the sum of the all probability Pi, I equal to 1 to n, if you do the n measurement, should be 1. And what you have to do, you have to average out these values in order to get the final values. So that is known as your expectation value. So that I have said here. So when we do measurement, we have to take weightage of the individual measurement and you have to average it out. For example, the Q1, Q2, Q3, Q4, these are the observed value, and P1, P2 are the relative probability, and this angular bracket that represents is known as your expectation value that you expect when you do final observation. And the sum of the total probability is one, that will be Pi Qi. Okay, the relative the probability, and then Q1, P1, Q1. That means, let's say you are measuring at time t equal to 1, 2, 3, 4, 5, 6, and so on. Similar position 1, 2, 3, 4, 5. The corresponding probability, measurable quantity, probability, measurable quantity will give you the expected value. So is it clear to everybody how you get final observed value from a quantum system? And this Q1, Q2, Q3, that is known as your eigenvalues associated with the measurement. What is the eigenvalue? So let's discuss that one. So that we have already talked about. So we know that any measurable quantities in quantum physics can only take some discrete values with certain probability, discrete values, rather than the continuous value. For example, discrete energy level. And what we'll have, since it will take the discrete value, like simple harmonic oscillator, which is a classical system, the energy is continuous. For example, potential energy variation will be like this, kinetic energy will be value like this, and total energy will be constant like this, which is a continuous, right? But in quantum system, we know we'll have a discrete values, and the classic example is the discrete energy of the system. So it means all the possible value, all the values, discrete values are not allowed. All the discrete values are not allowed. You cannot take the arbitrary. So which discrete value will be allowed? It will follow some rules. Okay, and that this set of discrete allowed values associated with the measurable quantities, namely that I talked about Q1, Q2, Q3 and so on, these are known as the eigenvalues. So in mathematics language, eigen means the measurement allowed values, which is validated values. And this is known as the eigenvalues associated with the measurable quantities. For example, the hydrogen atom. The energy spectrum is like this, minus 13.6 n square. U1 minus 13.6, E2 minus 3.4 and so on. So this is known as energy eigenspectrum. So these are the allowed values. Minus 13.6, minus 3.4, they are allowed. Minus 12.5, this value is not allowed. So some of the values that associated with the measurable quantities is known as your eigenvalues. So in fact, this is known as the eigenvalues Q1, Q2, Q3, Q4. These are allowed values and therefore they are eigenvalues. And as I said that when an operator, in order to get an eigenvalues, let's say Qi, the operator should act on the wave function, certain part of the wave function, and that wave function is known as your eigenstates or eigenfunctions. So it means in order to get the eigenvalue, discrete allowed values, the wave function must act some part of your wave function, the total wave function psi I, and this part is known as your eigenfunction. Here psi I is the eigenfunction. Then you might make ask question. Then what is the relation between this eigen wave function psi I and total wave function psi RT? What is the relation between them? Okay, so I represents the eigenstates or eigenfunctions. For example, psi1, psi2, psi3, these are eigenfunctions and their corresponding eigenvalues q1, q2, q3, q4. Okay, and the total wave function psi r2 is in fact the linear combination of all possible eigenfunctions. That means the total wave function we are talking about here, psi rt. So they must be, will be, let's say we have, let's say p1 psi1 rt of course plus p2 psi2 rt to pn psi n rt. Okay, so the linear combination of all possible eigenfunctions. Okay, so this is the relation between the total wave function and the eigenfunctions. So that I have written down here. So this is the total wave function and this psi1, psi2, these are, and it also validate the principle of the superposition. By the, am I audible?
Yes, sir.
Yes,
Hello?
sir.
Okay.
Yes, sir.
So if you remember in optics chapter, we use the principle of superposition. So you can think these are individual wave and the linear combination will give a superposed wave. Similarly, so this eigenfunction, if you take the linear combination, that will describe the whole system through this complete wave function psi rt. Okay, and AI is the weightage of the individual wave function. Okay, and this, the probability of any measurable quantity that we are talking about at a given instant of time pi will be decided by the AI square. Okay, the coefficient as or weightage of the individual eigenfunctions. Probability of, let's say this is ith eigenfunction, eigenstate contribution to the wave function. How much the ith eigenfunction or eigenstate will contribute the total wave function will be decided by this factor pi, which is ai square. Okay, and then the expected value that we have already discussed. So this is the very quick and more fundamental about measurable quantities, the mathematical formulation, and how one can understand that how one will measure the observable quantities, measurable quantities from a quantum systems. Okay, so it means we have to solve Schrodinger equation in order to get the wave function, and an operator must act on wave function in order to get the measurable quantities. And when we do the measurement again and again, right? So then we'll have to average it out in order to get final expected value, which is represented by angular bracket. And then the discrete values which are allowed. The discrete values, that means in a measurement we'll have a discrete values, which is the fundamental principle of the quantum, fundamental outcome from a quantum system. We have a discrete values, and if we have collection of these discrete allowed values, they are known as eigenvalues. And in order to get these discrete allowed values, which is, as I said, they are known as eigenvalues, the operator must act on some portion of the wave function, and that some portion is known as your eigenstates or eigenfunction. That means for each allowed discrete values, there must be corresponding eigenstate or eigenfunction. And if we combine with linear superposition, these eigenstates or eigenfunction will get the final or total wave function of the quantum system, and that will describe, that will contain all the information of the quantum systems. And that's the procedure way people do measurement from a quantum system. So is it clear? Yes or no? Am I audible? Hello, am I audible?
Yes, sir, you're audible.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so let's work out a few problems to clarify furthermore. Okay, so here are some problems, and you might have seen in your assignments. Find the eigenfunction psi x for the operator this. So this is an operator, and you have to find out the eigenfunction. So how many of you have done this problem? Assuming this, that means the q psi x will be q psi x, because this is the eigenfunction, and then what we'll have, x plus x psi x plus d over dx psi x equal to q psi x, and then you have to solve this equation. Okay, so it's the differential equation, and you have to integrate in order to get this psi x. So it is first order ordinary differential equation, and you solve, you will get psi x. That will be your eigenfunction. Calculate the energy of a free particle. How many of you have done this problem? I'll do it this problem. So energy, we have to have energy operator, is bar del over del t, and psi x will have psi x, because the potential energy is 0. Okay, and for free particle, psi x equal to a e to the power I kx, or you can write a sin kx plus b cos kx, and you can use it and solve it. Finally, you will get the energy. Okay. So in fact, this has been solved here. Okay. So actually, you have this. You have to rearrange this q minus x, then this. So it means the eigenfunction is c e to the power I kx minus x square over t. So similarly, here, okay, equal to ek. In fact, we have solved in 3 dimensions. This is the energy operator, and okay, sorry. So and by using this equation, as I said, that this is a energy operator, and you can have h bar square over 2m, and you have to substitute it. By the way, you can hear me, right? Am I audible?
Yes, sir.
Yes, sir.
So now that's exactly we have done. We have energy operator, because this is minus IH bar del over del t, as I have said above. You have to substitute it, then there you will get the energy will be h bar square k square over 2m. Okay, and the third problem is very important in order to understand what is eigenfunction, what is total wave function, what is linear combination, what is the expected value. So the wave function, this total wave function, psi, capital Psi of a system is a linear combination of eigenstates psi 1, psi 2, and psi 3. So it means we have 3 eigenstates, psi 1 and psi 2. And this is the total wave function. The first question, is it a valid wave function? I will check whether it is a valid wave function or not. So it means the sum of the total probability is 1. So the P1 is 1 over 2, P2 is 1 over 3, P3 equal to 1 over c. So the P1, P2 plus P3. Is it 1? If yes, 1, that means yes. So this is a valid wave function. If it's not equal to 1 or greater than 1, that means it is not valid wave function. If it is less than 1, that means there must be another eigenstate, the fourth eigenstate, because the sum of the total probability is less than 1. If it's greater than 1, that means it is not a valid wave function. So since this case it is 1, that means it is a valid wave function. And the second question is, what is the probability of the system being in the state given by psi 2? That means when we do measurement, what would be the probability that we'll get the information or the measurement any from this psi 2 state? The probability will be simply 1 over 3. Whatever the information we'll get from psi 2, it will be have contribution 1 over 3. Is this clear to everybody?
Yes, sir.
Yes, sir.
Yes, sir.
So now let's look at this problem. So 2 over 5, 1 over 5, 3 over 10, and 1 over 10 are the probabilities that the system be in the 4 eigenstates represented by psi 1, psi 2, psi 3, psi 4. What would be the wave function psi? The first thing you have to check whether the sum of the total probability 1 or not. In this case it is 1. So therefore no eigenstates are missing. So this will have therefore 4 eigenstates. And what would be the wave function? Psi 2 over 5 psi 1 plus 1 over square root 5 psi 2 plus 3 over 10 square root psi 3 plus 1 over 10 psi 4. Because the coefficient C1 will be square root over P1. Okay, so this will be a total wave function. And the fifth question is, this is also associated with the problem number 3. The probability that the system can be in state represented by psi 1 and psi 2, this. Write the wave function of the systems. First of all, you have to check whether the sum of all this probability 1 or not. If it's 1, that means it's correct. If it's not 1, that means if it's greater than 1, it means it is these eigenstates are wrong. And if it's less than 1, it means one more eigenstate is missing. So in this case it is 1. So therefore we can write down the wave function, and then the wave function will be 1 over 2 psi 1, 1 over root 3 psi 2 plus 1 over root 6 psi 3. And then what would be the expectation value associated with the energy? Energy eigenvalues, what would be the energy expectation value if the eigenvalues are 4, 6, 9? How will calculate? The expectation value energy, the angular bracket E, will be the probability, the P1 E1, P2 E2 plus P3 E3. What is P1? 1 over 2 into 4 electron volt, 1 over 3 into 6 into 1 over 6 into 9. Okay, so this will be 2, this will be 2, sorry, this plus, this will be 1.5. So the energy expectation value is 5.5 electron volt. That means we do measurement, and these are the energy we get from the individual eigenstate, and this will be this at a given instant of time. And the next instant of time, this probability will also evolve. Okay, and if the probability will be, let's say, 1 over 3, 1 over 2, and 1 over 6, and what is the energy expectation value? We have half in 1 over 3 into 4 plus on 1 over 2 into 6 plus 1 over 6 into 9. So in this case we have 1.332 plus 1.5. So we have 4.83. So the energy expectation value in the next instant of time will be 4.83 electron volt if the probability is here, because the probability evolves over time. So now you can see, right? So how the energy expectation value changes over time since the relative probability changes. Okay. So this case 5.5 electron volt. So now you can realize more or less about how one can do measurement from a quantum system and how this measurement changes over time because the relative probability changes. So therefore the expectation value changes. So this is all about elementary things of quantum physics, right? And in the next class, we will start with time independent Schrodinger equation, because in practical purpose, as I said, or the problem we are going to solve, they are independent of the potential does not changes over time. So therefore we should begin with time independent Schrodinger equation. There we'll see how the Schrodinger equation will give you the wave information of the wave function at different instant of time. Therefore the relative probability also change over time. And there we'll get, we have been talking about the discrete values of the measurable quantities, or in particular the discrete energy associated with the quantum system or quantum particle, and there will derive explicitly, right? So the discrete energy levels, they will appear automatically when we solve the Schrodinger equation. That means the quantum system will have discrete energy spectrum when we solve Schrodinger equation. So there are exactly 5 solvable, problems in quantum physics. Right? That means we can solve, exactly without any approximation. So we'll do one by one in the next class. So any question or doubt on today's lecture? Am I audible?
Yes, sir.
Yes, sir.
Any question? So I hope everyone is doing assignments. So, so those who
Sir,
have
you
not,
haven't given any assignment for quantum physics yet.
Yes, sir. We got
Yes,
only two
sir.
assignments.
Yes, sir.
quantum physics assignment is not given.
Yes,
No,
No,
sir.
sir.
Not given, sir. Not yet given.
only first two.
Okay. Okay, I'll post by today. Okay.
Okay, sir.
Okay, you'll find varieties of problem. I'll show you. Mm, mm, for example, where is this assignments? I have not posted it. Okay, so these problems we have solved today's, right? Problem number 18, 19, even if 20, right? Even if 22. 21
Yes.
also we have also solved, okay? So you'll find varieties of problems. So there are 32 problems. So by the way, so I'll post it by today. Okay. So you solve these problems and you have already seen, right? So some of the problems you'll find in your exam. So it is essential to solve it. And in addition to that, for assignment, we have also 5 marks. Right? So we have, maybe 3, 4 assignments. And if you submit this assignment, you'll get 5 marks. So each assignment will carry 1 or couple of marks. So the total mark will be 5. So if you submit, you'll get 5 marks. Otherwise, you'll be evaluated 95 rather than 100. So it is essential to do each and individual problem in the assignments. You'll get double benefited. You'll get some problems in your exam as well as you'll get mark by submitting the assignments. Okay, so I should stop here and I'll also post assignment now and you have to solve it. And in the next class, as I said, we'll begin with Schrodinger equation, time independent Schrodinger equation, and there we'll show how we can get, the wave function and how the discrete energy level appears for a quantum system. That will discuss all this in great detail in the next lecture. So bye everyone.
Thank you, sir.